Hi folks, like Tamara said, I'm Rehan Durrani, and today I'm going to be talking about how to maximally parallelize the entire pandas API. People love pandas. It's flexible and easy to use with over 600 APIs that allow for rapid prototyping, which leads to its wide adoption. The problem is, pandas doesn't scale. It requires all of your data to be in memory and single-threaded, which means that the runtime can increase dramatically even on simple pipelines when the size of your data increases. Enter Modin, a distributed drop-in replacement for pandas. But before we get into the details of how we implement Modin, let's take a step back and talk about why data frames are interesting. What is it about data frames that make people love them so much? The short answer is that data frames offer a wide variety of operators from different data modalities combined into one easy to visualize representation of tabular data. In other words, like we said earlier, data frames are flexible. And we really begin to see this flexibility when we take a look at what a data frame is and what it can do. Formally, a data frame is an array of tabular data along with a set of column labels that are often semantic in nature, a set of row labels that are similarly semantic in nature, and a schema that maps the name of each column to the type of data it contains. Like arrays, data frames have an implicit ordering on position and support positional random access and the transpose operator from linear algebra. But like databases, they also support label-based access. Data frame schemas are flexible. Say your coworker gives you a CSV that they want you to analyze. You don't have to spend your time going through the CSV and manually determining how many columns there are, what the name of each column is, and what the type of each column is. As most, if not all, pandas users will know, pandas will automatically infer a schema on your data frame during ingest. And if you decide that that schema is true restrictive, or maybe you want to change types or add columns, you can always change that during your workflow fairly easily and pretty rapidly. So if everyone loves data frames so much, why are we having this conversation now? Data frames were first introduced to the Python ecosystem more than 10 years ago, so why don't we see more scalable data frame systems? And the answer lies in three key challenges. The first, ironically, is their massive API. Pandas has over 240 unique operators, which makes it very hard to optimize each by hand. The second has to do with parallel execution. As data science practitioners will know, data frame operations often involve accessing data in different ways, whether it be along the rows, along the columns, or along the cells. Each of these three types of data access requires different parallelization schemes in order to effectively optimize them. The third has to do with variable data shape. Databases are tall and skinny. They have many rows and few columns. Thanks to the transpose operator, data frames can be not only tall and skinny, but they can also be wide and short, which induces additional complexity in the system. On the Modin team, we had three key insights to help us resolve some of these challenges. Well, all these challenges. The first is our data frame decomposition rules that allow us to effectively partition data frames. The second is the principle of metadata independence that allows us to more efficiently compute data frame operations. And the third is our data frame algebra, a minimal set of 16 operators that we can compose to form any data frame query. In the next couple of slides, we'll talk a little bit about each of these approaches and how they help us resolve the challenges in the previous slide. First, data frame decomposition. Why do we care? When we're doing a data frame operation, say we're taking the mean of all the rows, we can parallelize that along the rows. If we're doing an operation like the mean of each of the columns, we can parallelize along the columns. But we can't do the opposite. I mean, you could do a two-phase reduce, but for the sake of this example, let's say we want to parallelize along the columns. It wouldn't really make sense to do a mean operation along the rows, parallelize across the columns. Each operation on a data frame has a certain level of parallelism, whether it be along the rows, along the columns, or along the cells. And using our data frame decomposition rules, we can partition our data frame effectively to take advantage of that native parallelization. So let's take a look at this data frame. When we talk about data frames, we often talk about two axes, the row axis and the column axis. They function pretty similarly to the x and y axis in the Cartesian plane. The row axis runs top to bottom, and the column axis runs left to right. We can decompose along each axis, and that just means to split the data frame into data frames that contain one or more elements along that axis. So if I were to do a column-wise decomposition, I would take this data frame and split it up into a list of data frames, where each new data frame has one or more of the original data frame's columns and all the rows. Similarly, I could do a row-wise decomposition, where I take this data frame and I split it into a list of data frames that contain one or more of the rows of the original data frame and all of the columns. I can even apply these decompositions recursively, going all the way down to a cell-wise granularity, where each data frame is a single cell from the original data frame. Thanks to this, I can more effectively partition my data frame. If I have an operation that's parallel along the rows, I can use a row-wise decomposition to come up with a row-wise partitioning system. If I have a column parallel operation, I can do a column-wise decomposition and get column partitions. If I have a partition that's parallel along the cells, I can recursively apply column-wise and row-wise decompositions to get block partitions, which are similar to cell-wise decompositions, but just not as granular. And this way I can maximize the parallelism across any operation. Our second idea is that of metadata independence. The key here is that metadata can be fairly expensive to compute and also pretty dynamic. It can change quite frequently, but we don't always need to eagerly maintain metadata. Let's talk about a concrete example. Take position, for example. If this were my data frame, in order to compute the position, say to know that this is row 0 and this is row 1 and this is row 4, I'd need to do a join of all the partitions along the vertical axis because position is directly tied to how the data is laid out, right? But this can be fairly expensive. I don't always need to do this. So say I have the following pipeline. I add 1 to every cell in my data frame, I select every other row, and then I add 2 to the new data frame. This operation doesn't change position. This operation does change position, but importantly, this operation not only doesn't change position, but doesn't care about position. So there's no point in eagerly materializing my position between these two operations. Instead, I can wait till I get to an operation, perhaps this one down the line again, that does require position, and then materialize my position, allowing me to amortize the cost of maintaining position across all of these operations. The third idea is our data frame algebra. It's a minimal set of 16 operators that can be composed to form any data frame query. There's 3 types of operators. The first are low-level operators, like map, that physically manipulate data. The second are metadata operators, like toLabels, that transfer columns from the array of data into the into the row labels or column labels. And the third is relational operators that we borrowed from relational algebra, like sort or join or union. And the neat thing about this is since I only have 16 operators, it's very easy to, well, perhaps not very easy, but it's a lot easier to hand optimize each of these 16 operators than it is to hand optimize 240 plus operators, right? And thinking further, if we have queries that are compositions of these operators, it's a lot easier to understand how to compose or reorder 16 operators than it is to understand the relationships between 240 unique operators. So now we've covered how, in theory, to design a system, how do we get down to actually building it, right? How do we design a scalable data frame system? The answer lies in modularity. Modin has 4 layers. The first layer is the API layer. This layer mimics your favorite API. In this case, we have the pandas API, but you could always extend it to have the SQL API or some other API. The next layer is the query compiler layer. This layer translates between the API layer and our algebra layer. It's basically like a transformer, basically. We go from this really wide API layer to this very narrow algebra layer. The third layer, as we discussed, is our algebra layer. And this is the layer that knows how to do the sort, the map, the join, but it also understands things like metadata independence and lazy metadata materialization. The final layer is the execution layer. And this layer understands how to talk to execution engines like Ray or Dask, as well as how to physically manipulate partitions in order to accomplish what the algebra wants. Say we want to do a map over rows, the execution engine understands how to get the partitions to form row partitions in order to do that map. So how does Modin stack up against the competition? If you take a look at Modin functionally, we can see that we have over 90% coverage of the pandas API, while Koalas, which is Spark's pandas offering, and Dask data frame collectively have less than 60%. If you take a look at performance, we can see that Modin consistently outperforms Koalas, Dask, and pandas on operations like fill and ate that are supported by all 4, and outperforms pandas on operations like median, which are complicated for Koalas and Dask to do because of their partitioning strategy. So ultimately, what's the end goal here? At Ponder, our vision is pandas on everything, not just your favorite distributed execution engine like Ray or Dask or Spark, but also on top of your favorite database like Postgres or Snowflake. If folks have any questions, please feel free to reach out to me. My contact info is here. And make sure to check out this QR code. You can try out a free trial of Ponder, our platform. Yeah, I can take any questions now if folks have questions.
I just realized I was muted. I was talking to you and apologize for that. Juggling a lot here. Carlos has a question. If you can, I don't know if you can see that on the screen.
Yeah, I can. Sorry, I wasn't trying to see questions. Yeah, so Carlos, this is a really good question, and the answer is yeah. So, because we designed Modin to be modular, you could actually plug in any layer you wanted. If you want to write your own query compiler, you could. If you want to write your own execution engine layer, say you have, your own execution engine that you've written, you could do that. But we're actually at at Ponder, we hope to have more APIs than just the pandas API, perhaps even a custom Modin API that dictates how we think dataframes should work.
Okay.
So Neil asks, can Modin be used out of... Sorry, Tamara, did you want to read it or should I read it?
No, go for it. You're great.
Awesome. Thank you. Yeah. So Neil asks, can Modin be used out of the box on Databricks, and would you recommend using it on Databricks? So that's a really good question, Neil. And the answer is it kind of depends on what you mean. Do you mean to use Modin on top of Databricks as in... So the way I understand it, Databricks has a notebook offering that it runs, that basically is the front end for its cluster. So could you run Modin on top of that? And the answer is yes, although we don't actually have a execution engine yet for Spark. So you would have to basically install maybe Ray or DAS or some other execution engine on top of your cluster and run it like that. So would I recommend using it on Databricks? Kind of yes and no. It really depends on how whether you have the resources or not to do your own cluster management. So right now, our Ponder on top or Modin on top of databases is in the trial stage. So that's what that QR code right here is for. Sorry, can people still see my screen? I hope so. Yeah, so you do need a distributed execution engine to run Modin if you're not using the trial that QR code goes to. So you need to basically stand up your own execution engine on top of that cluster. So whether I would recommend using on Databricks bare metal, it kind of depends on whether or not you have the resources to manage your own cluster. Like if you already use Databricks for your cluster management, then I think it makes sense to just go with Databricks and stand up a lightweight Ray or DAS cluster on top of your Databricks cluster. If you have it, if you have an AWS account and a bunch of credits, then maybe it makes more sense to do that. I hope that answers the question, Neil. And feel free to reach out to me on Discord or Twitter or the Modin public Slack if you have any follow-ups. Jasdeep, you ask, what does it not cover? I'm sorry, I'm not quite sure I understand the question. Could you maybe clarify a little bit?
We can switch and see if they clarify.
Sure. So what does it mean? Yeah, actually, so that's what that QR code is for. Actually, sorry, let me read the question. I just got very excited because this is some really awesome work that folks at the Ponder team have been doing. Mark asks, does it mean you can run Modin on Snowflake as it stands today? The answer is yes. We're still working on some of the kinks and making sure we can get up to that 90% API support. But if you go to this QR code, you can sign up for a trial and you can run your workloads on top of Snowflake today. Yeah, you can do it right now if you want. In fact, I encourage folks to do it right now. It's some really awesome work that some of my colleagues have been working on at Ponder. It's very exciting stuff. Aditya asks, how easy is it to use Modin data frames in machine learning libraries like XGBoost, LightGBM, etc.? That's a really great question, Aditya. And this kind of has to do a little bit with two things, kind of like how well we implement the interface that Pandas supports, as well as our exchange protocols. So in cases where these libraries already support using Pandas data frames natively and they have hooks, I think it should be fairly easy to integrate them because we support the exact same API as Pandas. And if there is an API that Pandas has that we don't have implemented in a distributed fashion, we default to Pandas. And what that means is we gather all the data onto the head node, run it in pure Pandas, and then distribute the thing back again. So if the library just uses Pandas under the hood, it should work out of the box. If the library uses something like NumPy or something like that, where it requires an exchange protocol from Pandas to something else. Again, since we have that support for the Pandas API, we have these exchange protocols written. You can convert to NumPy. You can convert to, any other type of data representation you want. An XGBoost D matrix. We have actually a custom implementation of XGBoost on top of Modin. So with XGBoost, it'd be even easier to run it, but it should be fairly easy to run. In fact, I think Alejandro is maybe here right now. Alejandro is our solutions architect at Ponder, and he's worked with some folks who have used stuff like LightGBM and XGBoost on top of Modin, and he could probably elaborate some more on what that experience has been like. I will say also, towards the future, we're hoping to have even more APIs that are supported on top of Modin. So not just the Pandas API, maybe other really popular data science libraries, which would make it really convenient to run stuff like XGBoost and GBM. Sorry. Blue Tyson asks, what happens if you combine with Dask? Sorry, do you mean what happens if you use Dask as an execution engine? I'll answer that question because that's a very interesting question. If that's not the question, I apologize. Feel free to ask again with a little bit more clarification so I can understand a little bit better. So if you use Dask, we're just using Dask as a distributed task management system. So just to handle running a cluster and scheduling tasks. So it would be the same as Ray, it'd be the same as any other distributed task management system. If you mean like what happens if you try and interoperate between Modin and Dask, I'm not actually sure that Dask supports that. I think you have to be like fully in the Dask data frame platform in order for it to work. But maybe we can return to this question in a little bit when we have some more context. Sorry. Oh, perfect. Yeah. So Alejandro was responding to the Databricks question. So Alejandro, Solutions Architect, just chimed in. He says you can install Ray on Databricks cluster by using an initialization script. Then Modin will take advantage of the full cluster. So yeah, if you use Databricks to do cluster management, it's fairly easy to install Ray or Dask on top of that, and then just run Modin on top of that.
This next one is a two-parter. So here's the first part.
Okay, I understand it covers 90% of API only. All right. Oh, the question is what is the I see. My bad. I totally misunderstood. So actually I will say that 90% number is just me reading this graph. It's actually a lot higher in practice. It's like 95%, I think. I just, it's always better to hedge a little bit and give a lower number, right? The 10% it doesn't cover is stuff that we're working on every day. So one really salient example actually is sort. So one of the things with the distributed execution engines we use under the hood is they're not really great for shuffling data across partitions. As you can imagine, if you have a bunch of different nodes and they all have a bunch of memory that they keep to themselves, they don't really want to share data across those nodes and shuffle data across partitions. So operations like sort can be fairly expensive on top of any distributed execution engine. So that's like an example of one of the APIs that we don't cover. Although I actually have a PR in the works to natively support sort from Modin, and so say tomorrow, or I guess later today, my time. I'm in California, so later today, Friday morning, maybe Monday or Tuesday, we will actually have a little bit higher support, and we'll actually support that. But yeah, in terms of like what we do and don't support, you can actually check out the Modin docs, and we have a list of supported APIs right there. Right there, yeah. So you can see here, like stuff like transpose, abs, add, they're all fully supported, and then like ag is like partially supported, align is supported. Sorry, like align is supported like partially. So this can help you figure out exactly whether what you want to do is supported or not. And again, if it's not supported, it doesn't mean we break. We just default to pandas, and then you can continue with your workload however you'd like. Hopefully that clarifies. Awesome. Yeah, Alexander asked a really good question. I imagine there are cases where we must change the pandas code to make the most of Modin. Do you have some general rules for that? And that's a really good question, and that's actually the subject of some open research we're doing. So I guess first I'll answer the question at face value. Are there cases where you need to change pandas code to make the most of Modin? And the answer is it kind of depends. Yes and no. So there's cases where you could be doing something like, for example, iter rows, which is not really efficient in a distributed computation environment because, we need to transform those block partitions into row partitions, and then we have to iterate over each row and then iterate across the partitions. And so in cases where you're doing stuff like that, it might be better to rewrite your query. But this is kind of the same as like with SQL, right? Like there's generally like smart and not great ways to write a query that are more or less efficient. In terms of, do we have general rules for that? Not off the top of my head. I think in general, well, okay, yes, kind of. So in general, you kind of want to try and maximize parallelism however you can, right? So if you're accessing rows in a for loop, right, you don't necessarily want to be doing that. Instead, you could try like an apply, right? The data frame apply, which is row parallel, right? If you're modifying a cell at a time, instead of doing that, you can try like an apply map, which would map over all the cells, right? So in general, we want to kind of aim for those pandas APIs that are the most parallel wherever we can. And then in terms of like the broader question here, so this is query optimization, right? So one of the goals with designing with the data frame algebra was actually to mimic how SQL doesn't really punish users for poor queries, right? Like if I was working on a database and I wrote a query where I did a join and then I did a filter, right? Like objectively, that's not the best way to write this query, right? It would be better to do the filter than the join because the cardinality of the things I'm joining is lower, right? And under the hood, the SQL database knows this, and so it's going to rewrite my query so that we do predicate push down, right? And we push the filter up ahead, right? So with the data frame algebra, we actually hope in the future to be able to do the sort of thing with pandas queries. Basically, to take a pandas query that the user writes and then leverage the think time where users are inspecting the contents of the cell in order to go like, okay, like I notice they're doing a join between two data frames and then they immediately drop call rows where like this value is true. So let me first do the drop of the rows and then let me do the join. So yeah, hopefully that answers the question, Alexander. And we also have the Modin Slack. if you go to the Modin GitHub page, there's even if you go to the docs, there's like a link to the Slack, and then that's the PyPy link. I'm sorry. That's the Slack link. I'm not wearing my glasses. So the Slack, you can always post questions like this if you have a specific thing where you're like, hey, like I'm running this and it's not really working as I'd expect. Like, what do folks think? You can always post it there, and we're happy to help out always. I see. Blue testing says that or delayed Modin tasks on Dask compared to Dask data frames, perhaps. So again, I'm not sure I'm understanding the question fully. It sounds like perhaps you're asking for a comparison of like how does Modin on Dask work versus how do Dask data frames work, perhaps like performance wise or functionality wise. I will say Dask data frames require, I believe it's row partitioning. I'll have to double check. I'm not sure off the top of my head. And so the operations that Dask supports is actually fairly limited. Like in that graph where we took a look at performance, you can see here, Dask doesn't have a median operation, right? And so both in terms of performance and in terms of like functional, like how much you can do, Modin is more expressive because you don't have to automatically manage partitions. In fact, I was talking to someone in the past who was using Dask data frames in addition to Modin. One of the things I really liked about Modin is Modin automatically handles how many partitions to make and how to partition and managing the skew of partitions automatically, right? So with Dask, for example, you take the data in Dask and then you need to manually partition it. And if your partitions get skewed, you have to go in and be like, okay, like let me rebalance these partitions in order to make sure there's no skew in the size of each partition, right? With Modin, we have a bunch of concepts like virtual partitions in order to help the user automatically rebalance the partitions under the hood. So you don't even have to worry about partitions. Like we have a heuristic for determining the number of partitions is basically equal to the number of threads in your device, and then we manage making block partitions, making row partitions, making column partitions, and making sure those partitions are roughly evenly sized, all without any worry. So there's a lot of flexibility and there's a lot less worry that you have to have as a Modin user than as a Dask user. Alexander, that's a great question. On the SQL analogy, is there a way to view the query plan? That's a great question. So on top of the work we're doing with Modin on top of Snowflake, there is a way to view this query plan. For now, not quite. Okay, I'll correct myself. Yes and no. So there is an experimental branch of Modin that we're working on, where we do actually formulate these query plans, and we do have, in fact, one of somebody on my team just recently added a feature to visualize these query plans. But this isn't publicly released yet, just because we're still working on some of the kinks with like being able to like form these query plans and translate them to all the algebra. But yes, in the future, like when we do have this fully working and published, there will be a way to view them. Interesting. I'm not so Blue Testing asked. Now I wonder about switching out an X-array. I'm not familiar with X-array. It seems like that might be an array API. I'm happy to take this conversation offline, but I'm not familiar with X-ray, so I don't think I can comment on that. Also, let me do this. That way, if folks are interested in checking out the QR code, they can see that.